far this chapter, we've been applying several different basic integration techniques. We're going to now get into a few more advanced integration techniques. At the end of this lesson, you'll be able to evaluate an integral using something that's called integration by parts. All right, I'm just going to start with a theorem, which you'll notice says the integral of u dv is equal to uv minus the integral of v du. We are going to use this when we're actually doing integration by parts, but I just wanted to show you where it comes from. So let's say I start out with some function u and some function v, and I multiply them together, and I decide that I'd like to take the derivative of that. Well, if you notice, if I'd like to take the derivative of this, since I had multiplied u and v together, I'm going to have to use the product rule, which would mean I'd name my f and my g. My f prime, the derivative of u, would just be u prime, or I could also call it du, same thing. And then my g is v, so my g prime would be v prime, or I could also refer to it as dv. So if I use the product rule for this, I'd have f prime times g, so I'm going to have du times v, so another way of writing that would be v du, plus f g prime, u times dv. All right, now let's just say for fun, I do not want the derivative there. So to undo the derivative, we know that we're going to have to take the integral of every single part. When I do that, my derivative and my integral would cross out, so I'd just be left with uv, and then I'd still have the integral of v du plus the integral of u dv. Okay, now let's just say for fun, we decided we want to solve for this. So we would subtract v du from both sides. So if I solve for that, notice I'd have the integral of u dv is equal to uv minus the integral of v du. And notice that brings us to our theorem. Okay, that's an integration by parts theorem. If we have an integral that started out using a product rule, if we're going to take the derivative, we would use the product rule. We probably are going to use integration parts to find the integral. So we are going to specifically use this formula right here every time we do integration by parts. All right, some guidelines for using integration by parts. We're going to try letting dv be the most complicated portion of the integral that fits a basic integration rule. Then u will be the remaining factor of the integral. We'll try letting u be the portion of the integral whose derivative is a function simpler than u. Then dv will be the remaining factors of the integral. Well, I'm guessing that didn't make much sense to you, but basically what we're going to be doing is we're going to let u be one part of the problem, and we're going to let dv be another part of the problem, and then we're going to try to work out its parts and then put things together to come up with an integral. So we're just going to jump right into these problems and see if we can get that to make some sense. All right, this first one, you'll notice it says to evaluate the integral. I have the integral of 2x cosine x dx. If you recall, looking at the problem, I really want to see if I could do a u substitution or something first. I noticed that I can't separate it because it's not a plus, so I'm pretty much stuck. If I looked at this problem, if I were going to take the derivative of it, I'd use the product rule, which means it's a very good candidate for integration by parts. And I'm going to write down our integration by parts theorem right up here. So this was equal to uv minus the integral of v du. So that's what we're going to use to help us out. So I need to identify a u and I need to identify a dv. All right, u is usually something that if I take the derivative of it, I'm going to get a simpler part. So if I let the 2x be my u, that will work, and then the rest of it is going to be my dv. So this cosine x dx will be my dv. All right, so now the next thing that I need to find is if I have u, I need to find du, which would just be the derivative of u. The derivative of 2x would be 2 dx. And then dv, if I have dv, I just want v. So if I have a derivative and I just want v, I'm actually going to take the integral, and the integral of cosine is sine. All right, so I now have all of my parts. I'm now just going to apply it to the formula. So I basically have already done the left part. I've identified my u and my dv, so now I'm just going to be applying the right side of my formula. So first of all, it says to do u times v. So u times v will be 2x sine x minus the integral of v times du. So v is sine x times du would be 2 dx, and I just wrote it in order. We usually put our 2's first. Okay, so now from there, hopefully you notice that I can definitely take the integral of 2 sine x. So I'm going to have 2x sine x minus the integral of 2 sine x would just be negative 2 cosine x. And so then if I simplified that, I'll get 2x sine x plus 2 cosine x plus c. And then that would be my answer. Again, I was able to take something that I didn't know how to take the integral of, and I now have an integral expression. All right, let's try another one. Let's have the integral of x cubed ln x dx. Again, doing a u substitution is not going to get me anywhere. If I were to take the derivative of this expression, I would have to use the product rule, which once again makes it a good candidate for integration by parts. So once again, I'm just going to start by writing my formula. And I just get into the habit of doing that. So once again, I have to identify a u, and I have to identify a dv. All right, I would probably say when we started, x cubed is the one that would get simpler if I took the derivative of it. The only problem is I can't take the integral of ln x because we don't have a formula for that. So unfortunately, I'm just going to have to let the u be ln x. So this part is u, which means that all the rest of it in my problem has to be the dv. So x cubed dx, both of those will become my dv. So I've set up the left side of my formula. All right, so let's finish finding our parts. Du, the derivative of natural log, will just be 1 over x. And then v, if I'm starting out with the derivative and now I want v, would be the integral of this, which would be 1/4 x to the 4th. All right, we are now set. We have the left side set up. We're now set to actually do the right side. So uv, u times v is going to be 1/4 x to the 4th ln x minus the integral of v times du. So v times du will be 1/4 x to the 4th. Whoops, I forgot to put dx on that, sorry. 1/4 x to the 4th times 1 over x dx. All right, so I'm going to simplify this. This would be the integral of 1/4 x to the 4th times 1 over x. If I put a 1 under there, one of those x's is going to cancel and make it x cubed. And now from here, notice this actually is a pretty simple problem to take the integral of. So first of all, bring this down. All right, so I'm going to have 1/4 x to the 4th ln x minus the integral of x cubed would be 1/4 x to the 4th, but I already have a 1/4 there. So this is going to become 1/16 x to the 4th and then plus c. So once again, I was able to take the integral. All right, problem 3. Arc cosine x. All right, notice on this one, it really doesn't look like we have two parts. It doesn't look like we even have a u and a dv. It doesn't look like we'd use the product rule. Well, there are some instances where we'll actually use integration by parts when we don't have a product rule problem. This is one of them. We do not have an integral for arc cosine. We have one that equals the arc cosine, but we don't have an integral for it. But I do have a derivative for it. So once again, because I'm stuck and I'm not sure what to do, we are going to apply the integration by parts rule, which is going to be the integral of u dv is equal to uv minus the integral of v du. All right, we have no choice but to let arc cosine x be our u. So we have u equals arc cosine x. All right, so dv, the only thing left is the dx. So that has to be our dv. All right, du, the derivative of arc cosine, hopefully you're familiar with that, is going to be negative 1 over the square root of 1 minus x squared dx. And then v, the integral of dx, which really would be the integral of 1, is just going to be x. All right, so we're able to get going here. So have my left part set up. Now I'm ready to do the right side. So u times v. So I'm going to do u times v, which I'm going to have x arc cosine x, and then minus the integral of v times du. So negative 1 over the square root of 1 minus x squared times x dx. All right, I'm going to put a 1 underneath there, and I'm going to simplify it. I do know this negative on the inside and the negative on the outside can cancel, so this is going to become x arc cosine x plus, and then if I multiply straight across, I'll get x over the square root of 1 minus x squared. All right, now if I'm wondering what to do with this, the first thing that I usually like to try to do is a u substitution, which I will totally be able to do on this problem. So let's let u equal 1 minus x squared. and then du will equal negative 2x dx. Notice I have the x, I'm just missing the negative 2, so I'll put a negative 1/2 on the outside. So if I rewrite this, I'll have negative 1/2 on the outside. On the inside, if I were to bring this up top, I'm going to have u to the negative 1/2 du. So I'm ready to take the integral. I'll have negative 1/2. The integral of u to the negative 1/2 would be 2u to the positive 1/2. These 2's cancel, so I'm just left with negative square root of u. And if I rewrite that with my other part, my final answer is going to be x arc cosine x minus the square root of u, and my u in this case was minus square root of 1 minus x squared plus c. So once again, I was able to get an answer. All right, I'm going to go ahead and do this last one. I'd strongly suggest that you try this example on your own, pause the video, and then come back when you're done and see how you do. All right, this is a good candidate for integration by parts because I'd have to use the product rule to get the derivative of this. So we're going to once again write the formula u dv is equal to uv minus the integral of v du. Already identifying my parts, I'm going to let u be my x because the derivative of that will get simpler, which means the rest of it's going to be my dv. So dv will equal e to the 2x dx. All right, the derivative of u is equal to 1 dx, of course, and then the integral of e to the 2x. I'm just going to kind of go over here and do a little side trip. If I have e to the 2x, I really want to make this say e to the u. So u would be 2x, du would be 2, so I'm missing the 2, so 1/2 needs to go on the outside. So now this is 1/2 the integral of e to the u. The integral of e to the u is e to the u, so I'll have 1/2 e to the 2x. So the integral of this was 1/2 e to the 2x. And I will in class show you a little bit simpler way of doing that so we don't have to do that big old step every time we do the problem. Alrighty, I am now ready to use the formula. So u times v, I'll have 1/2 e to the 2x times x, and then minus v du, so I'll have 1/2 e to the 2x dx. So I'm pretty much all set to go here. I do know on this one, again, I have an e to the problem, so I really would like that to look like e to the u, so I'm going to let my u be 2x, which means my du would be 2 dx. I'd like a 2 there, but I have a 1/2, so I know I could multiply by 4, which means I'd put a 1/4 on the outside. So this now becomes minus 1/4 the integral of e to the u, and the integral of e to the u is simply e to the u. So I'll have negative 1/4 e to the 2x. I'm just now going to carry down what I've already found over here. I'm going to write that x in between those two. I personally think it just looks cleaner. So 1/2 x e to the 2x minus 1/4 e to the 2x, and then plus c. So hopefully now you can find the integral using integration by parts.